As we've seen over the last couple of days, when you find the equilibrium constant expression, you take the concentration of the products over the concentration of the reactants. And then we've even done an example problem already where when you're given the equilibrium concentrations, you can put those values into the equilibrium expression and you can solve for it. So for another example of that is you've got nitrogen and hydrogen reacting to make ammonia. It tells us that a mixture of hydrogen and nitrogen in a reaction vessel is allowed to attain equilibrium, and then the equilibrium mixture of the gases were analyzed, and you've got 7.38 atmospheres of hydrogen, 2.46 nitrogen, and 0.166 NH3. From these data, calculate the equilibrium constant Kp. So first of all, we know that Kp is going to be measured in terms of pressures. So it's going to be the pressure of NH3, and that's squared, over the pressure of N2 times the pressure of H2 cubed. So we're going to put those, they already give us those numbers, so we simply put those numbers into the equation. So the pressure of NH3 is 0.166, and that's squared, over the pressure of N2, which is 2.46, and the pressure of H2, which is 7.38, and that's going to be cubed. So now we get our calculator, and we take 0.166 squared divided by 2.46 divided by 7.38 to the third power. Looks like it'd be easier in scientific notation, and I get 2.79 times 10 to the minus fifth as the equilibrium constant. Now, those are pretty straightforward. There's nothing really tricky about those. They give you the equilibrium values. You put the equilibrium values into the equation. You get your answer, okay? Now, many times, though, that doesn't happen, okay? Many times when you're given a problem, what they'll do is they'll give you some of the initial values, or they'll give you some of the information, and they're going to make you have to find the rest of them, okay? And when that happens, and again, I've never seen a question that easy on the AP test, okay? That's simply plug the numbers in and get your answer, okay? What you're going to have to do many times dealing with equilibrium on the AP test is make what are called ICE tables. Okay? And an ICE table, those are three different letters, obviously. And the I stands for initial, the C stands for the change, and the E stands for equilibrium. Okay? And what we're going to do is we're going to take a problem, they're going to give us all the information that we need, and then we're going to find the rest of it. So let's just look at an example here. That's the easiest way to do this. So example 1 says, enough ammonia is dissolved in water, in 5 liters of water, at 25 degrees Celsius to produce a solution that is 0.0124 molar in ammonia. The solution is then allowed to come to equilibrium according to the following equation. So here we've got our balanced equation. Analysis of the equilibrium mixture shows that the concentration of OH minus is 4.64 times 10 to the minus fourth. Calculate Kc. So the first thing that we're going to do is we're going to write out the balanced equation, NH3 plus H2O, and again, that's a liquid, that's important there, in equilibrium with NH4 plus OH minus. Okay, and then what we're going to do is we're going to make a table below it. And we're going to put ICE. Some teachers do call these rice tables, where up at the top you have the reaction. I just think that sounds kind of dumb, so I just call them ICE tables. Okay, and what we're going to do is we're going to make a column for each of the reactants and the products. Now, the first thing we're going to do is if something is a solid or a liquid, we're going to remove it. So usually what I do is I just put an X through the ones that have a liquid or a solid in them. And now I'm going to start filling in what I know. So according to this, you're producing a solution that is 0.0124 molar in ammonia. Well, here's ammonia. And it says then the solution is then allowed to come to equilibrium. So this is before you've reached equilibrium. So that means initially the concentration of ammonia is 0.0124. Okay, and then it says analysis of the equilibrium mixture shows that the concentration of OH minus, so the OH minus equilibrium is 4.64 times 10 to the minus fourth. And then it says calculate the equilibrium constant at this temperature. Now, in order for me to calculate Kc, I know that Kc is going to equal the concentration of NH4 plus times the concentration of OH minus over the concentration of NH3. Remember, you leave out the water because it's a liquid. Okay, so right now, in order to calculate Kc, I need all of the equilibrium values. I need that last line filled in. I can't use the initial concentrations. I can't use the change in the concentrations. I have to use the equilibrium values. Okay, so I know that I still need to fill in this box right here and this box right here. And in order to do that, clearly there's some more work that I have to do here. So one of the things that's not mentioned in the problem but that we should know is that if I start with 0.0124, remember these are the initial amounts. If I start with 0.0124 molar ammonia and that's all that it says, then I can assume that that means that I'm not starting with any NH4 plus and any OH minus. Okay? So when they do that, if they just tell you about one of the reactants or the reactants in general and nothing about the products, you can assume that there are no products in this reaction at the very beginning. We're talking about before the reaction even starts. Okay, and now I can go, oh, wait a minute. If initially I had no OH minus and now I have 4.64 times 10 to the minus fourth, that means that the OH minus, again, this is the change here, that means that the OH minus went up by 4.64 times 10 to the minus fourth. Now, this change line right here is the only time that you can use stoichiometry to go from one thing to something else. Because we know that for every one NH4 plus, we got one OH minus. So if OH minus went up by 4.64 times 10 to the minus fourth, then NH4 plus had to have done the same thing. So 4.64 times 10 to the minus fourth. What if there was a 2, for example, right there in front of the NH4 plus? Well, then that would be double. So I'd have to take 4.64 times 10 to the minus fourth, and I would double it. Okay, it's not there, so I'm going to get rid of that too. Okay, and then over on the reactant side, something very similar. If these go up by 4.64, and again, it's a 1:1:1 ratio, the only difference is NH3 is a reactant. So if the products are going up, then the reactants have to be going down. So the change here is going to be going down by that same amount, 4.64 times 10 to the minus fourth. So for NH4 plus, it was 0. You're going to add, so clearly you're going to have 4.64 times 10 to the minus fourth. And then for NH3, we're going to take 0.0124, and we're going to subtract 4.64 times 10 to the minus fourth. And I get 0.0119, let's say. Okay, oh, and hey, what do you know? Now we have our equilibrium values. Now we can plug those numbers into the equation, and we can get our answer. So Kc is going to equal the concentration of NH4 plus times the concentration of OH minus. Since they're the same, I'm just going to write 4.64 times 10 to the minus fourth squared over 0.0119. So 4.64 times 10 to the minus fourth squared divided by 0.0119 equals 1.80 times 10 to the minus fifth would be our equilibrium constant for that reaction. Okay, now they're not all like that. That's a very common one that you can see here, but many times it changes. Let's just keep doing another example here, and you'll see every question's going to be a little bit different. So example 2 says sulfur trioxide gas decomposes at high temperature in a sealed container, producing sulfur dioxide and oxygen gas. Initially, the vessel is charged at 1,000 Kelvin with SO3 at a partial pressure of 0.5 atmospheres. So yes, you can use Kp with this as well. There's no difference there. At equilibrium, the SO3 partial pressure is 0.2 atmospheres. Write the balanced equation and then calculate the value of Kp at this temperature. So we're going to have sulfur trioxide decomposing to produce sulfur dioxide and oxygen gas. So we're going to need at least a 2 there, which means a 2 there, and I believe it's now balanced. Okay, and they give us some initial values, they give us some equilibriums, so we're going to have to make an ICE table here as well. So initial, change, equilibrium. What information do they provide us? They say that initially SO3 is 0.5. So SO3 initially 0.5. At equilibrium, SO3 is 0.2. So equilibrium SO3 is 0.2. Okay, and that's all that they give us. But again, if it was initially just charged with 0.5 atmospheres of SO3, it means there was no SO2 and no O2. So, and so now that's everything that we know. But again, once we know an initial and a change, we can go, okay, it was 500, now it's 0.200, so it went down by 0.300. Now again, here at the change part is where you have to be careful with the stoichiometry. If it goes down by 0.3 and it's a 2-to-2 ratio, then this one's going to go up by 0.3 because the ratio is the same. Okay? But then from SO3 to O2, there's half as much of the O2 made. So, and you can show this. You can say 0.3, just like if it were moles. Moles of SO3, and then you could say 2 moles of SO3 is going to make 1 mole of O2, and that just shows that, okay, we're going from 0.3 down to 0.15. Now again, it's a product though, so it's going to go up by 0.15. So equilibrium, 0.3, equilibrium, 0.150, because they both start at 0. And now we can get the equilibrium constant, okay, where K is going to equal the pressure of SO2 squared, so it's going to be 0.300 squared, times the pressure of O2, which is 0.150, over the pressure of SO3, which is 0.2, and again, there's 2 of them, so that also has to be squared. So 0.300 squared times 0.150 divided by 0.200 squared equals 0.338 as the equilibrium constant. Okay, so that's just, again, very kind of similar to that first one. But then notice we had those different coefficients in the balanced equation. Now, there will also be times, and this is where it starts to get a little bit fun, when the equilibrium constant K will be given to you, and you'll be asked to find the equilibrium concentration or pressure of one of the components of the equilibrium mixture. So they'll give you this number, and they want you to find one of these, and this is where the math can get fun. Okay, so again, you're still going to use an ICE table, but just like in any other instance with an unknown, like in algebra, you're going to use the letter X. So example 3 says a sample of pure NO2 gas heated to 1,000 Kelvin decomposes. So you got 2 NO2s in equilibrium with 2 NO plus O2. And the Kp value is 158, very large value. Analysis shows that the partial pressure of O2 It's 0.25 atmospheres at equilibrium. Calculate the pressure of NO and NO2 at equilibrium. Okay? So in this case, we know that at equilibrium, the partial pressure of O2 is 0.25. That's it. That's all that we know. So we know that Kp is going to equal the concentration of the products. So it's going to be the pressure of NO squared times the pressure of O2 over the pressure of NO2, which is also going to be squared. So there's a lot of information they don't provide us here. So it does tell us that, again, that at equilibrium, the partial pressure of O2 is 0.25. Okay, and it also says at the beginning, a sample of pure NO2. So again, that means that you're only starting with NO2, which means we weren't starting with any NO or O2 at all. So if we go ahead and make an ice table here, 2 NO2s in equilibrium with 2 NO plus O2, we know that initially there wasn't any NO or O2. And it says a sample. They don't even tell us how much NO2 we started with. So we can't really do anything there. That's kind of a question mark that we actually don't even really care about. Okay, but we do know that at equilibrium, the partial pressure of O2 is 0.25. So we know this value is 0.25. So that means that O2 went up by 0.25, which also means that if NO was 0 to start, and it's a 1 to 2 ratio, that NO had to have gone up by 0.50. So the equilibrium for NO, that's one of the questions, calculate the pressure of NO at equilibrium is 0.50. Okay? Well, now we know the Kp value. They give it to us right here, 158. 158 is equal to the pressure of NO, 0.50, squared. Don't forget that squared. Times the pressure of O2, 0.25, over the pressure of NO2 squared. And so that's our unknown. So now to solve for the pressure of NO2, remember when you have a denominator and you're looking for that, what the denominator is, you can switch. So I'm going to take 0.50 squared times 0.25 divided by 158. Okay, and that equals 3.96 times 10 to the minus fourth. So the pressure of NO2 squared equals 3.96 times 10 to the minus fourth. Obviously, I have to get rid of the squared. So the pressure of NO2, I'm just going to take the square root of that answer, and I get a final answer of 0.0199 would be my equilibrium pressure of NO2. Okay. Let's do one more, okay? So example 4 says calculate the equilibrium partial pressure of PCl3 in a 3-liter vessel that was charged with 0.123 atmospheres of PCl5. So I'm just going to make the ice table right below this here. So they give us the equilibrium constant. It was charged with, so that means we're starting with, so initial for PCl5 is 0.123. And that's all they tell us. We do know that if it was only charged with PCl5, that this is 0 and this is 0. And here's where it starts to get a little bit fun, okay? Because we do know, then that's it. There's no, like, we can use the equilibrium to figure out the change. That's all we know. We do know that PCl5, though, is going to go down by a certain amount. We don't know how much, but it's going to go down by a value that we're going to call x. Okay, well, if PCl5 goes down by x, what's PCl3 going to do? It's going to go up by the same amount because it's a 1-to-1 ratio. And so's Cl2, is you get an x there as well. Okay, Well, 0 plus x is just x. 0 plus x, x, and then 0.123 minus x is 0.123 minus x. So now we got a whole bunch of x's in here that we got to solve for. We do know the equilibrium constant though. So the equilibrium constant is 0.0121, and that's going to equal the pressure of the products, which are these two, and they're both x. So that becomes x squared. And then on the bottom, we get 0.123 minus x. Now, if you'll notice here, we're going to have to multiply both sides by this over to here. And what we're going to end up with is we're going to get to a point where we're going to have to use the quadratic equation. I know, you're excited about it. So am I. That's a lie. Okay? Now, I will tell you this. At no point on the AP exam in the last 40 years has a student had to use the quadratic equation, because we're going to make an assumption here. And the assumption that we're going to make is that x, and you can do this on the AP test, that this x value is going to be a very small value. And so what that means is we're going to assume that 0.123 minus x is going to be roughly equal to just 0.123. And what that's going to do is, yes, our answer is going to be a little bit off, but again, on the AP test, they're never going to require you to use the quadratic equation. So what we can do is we can say that x is small enough that when you subtract it from 0.123, it's just going to be really close to 0.123 still. So what that does, it makes our math way, way easier. So we're going to make that assumption that this here is close enough to just 0.123. So now I can just take 0.0121 and multiply it by 0.123, and that is equal to x squared. And so obviously to get x, I'm just going to take the square root of both sides, and x is equal to 0.0386. Okay, now what that means is it means that the equilibrium pressure of Cl2 is x, is 0.0386. The equilibrium pressure of PCl3 is 0.0386. And the equilibrium pressure of PCl5 is 0.123 minus 0.0386. So 0.123 minus 0.0386 equals 0.0844. Okay? And that is a good introduction to solving equilibrium problems that involve algebra.